So digital video is a code made of binary numbers, right? The point, so one of the points of learning binary numbering is that we can manipulate this code with math to take up less space. And we can do that by simply calculating numbers to make other numbers, right? So we'll get into that a little bit later, but the big thing about compression, the big thing with compression is it's a ton of math. The more compression you do, the more data you try to remove from a file and yet retain it as a video, the more math has to be done by the computer, by the camera, by whatever, right? So as we talked, I think before about shooting raw, when you shoot raw from a camera, there's no compression. So the camera can output the files fairly quickly. The problem is you're putting that work off till later. You're gonna have to do that compression somewhere else, right? In order to show it as video. You can't look at raw files as video. They're not video. They're just camera data, right? So a camera that's outputting JPEG, MPEG, very MOV, whatever the camera's outputting, is doing computing inside the camera, right? The more compression you're doing, the more math you need, the more batteries you require. There's a whole bunch of prices you're paying, right, for this extra math. So here's an example of something called on the right, just for the math nerds. This is something called discrete cosine transform. It's a mathematical principle which we don't have to understand, but you can see that there's a lot of calculations to be done to take a simple binary number and take the same amount of information that you get in a binary number, but use fewer bits for storage. Okay, so if you imagine all those bits we had in the last lesson as being numbers, you do a bunch of calculations to that, and what you do is, and here's how this works, this formula that you're looking at on the right is in all the equipment. It's part of the software of all the equipment in your, and this is a hypothetical, but in your chain. Everything has this formula in it. So when it is confronted with a number, it's doing a calculation to return that number to its original binary state. That original binary state takes up more physical bits. So, and this is the point of compression. Every bit of binary digit needs a specific discrete place to be. So if you think of eggs in an egg carton, you've got 12 eggs, you need 12 holes in the egg carton, right? And binary numbers are no different. If you have 8 bits, you need 8 individual storage bits, whether there's a 1 there or not. Okay? Because the computer expects there to be either a 0 or a 1. Remember, there's no such thing as an empty bit. So if a computer has an 8-bit space, then there's 8 bits of data in it. If the data at the moment is nothing, it's all zeros. But the point is all those zeros are a value and they all take up room in that 8-bit space, which means you can't put anything else in that 8-bit space. So what calculations like this discrete cosine transform does is it takes those 8 bits and does a bunch of magic with all these formula and puts the same amount of data in half the number of bits. But the only way to get the data back is to then do the calculation again in reverse. Okay, so that's compression. I've given you the entire story of compression in basically 2 slides. There's a lot more to it and we'll get into it. But understand that that's the basis for binary, is that we have to do this math. And so this is only one way. DCT is one of the more robust, as they say, which means it's a more fewer faults. It's a more reliable compression algorithm. So when you hear the word algorithm, that's what we're looking at right here, is we're looking at a mathematical set of instructions that are done to a binary number to make them take up physically less space. So you can take an 8-bit, and this is not, just so you're understanding, my example of 8 bits into 4 bits, that's not strictly true. There's no number, DCT doesn't come with a half or a quarter. It comes up with less. It depends on how much data it's manipulating. But anyway, let's just say for the sake of argument that using this formula, we can have 8 bits of information sitting in 4 bits of space. Well, now you can put twice the amount of information in that computer if you only have 8 bits. If 4 bits are now filled with the result of this formula, you have 4 empty bits that you can now put other data in, okay? And that's what compression has been trying to do and will be doing forever and a day. We're trying to get the same amount or more data into less and less space. And why is that important? Pretty obvious. You want storage to be smaller, physically smaller, because that space takes up physical space. right? Though when I talk about 8 bits of data, I know it's microscopic electron-sized bits, right? But eventually, when you have millions and billions of these things, they get pretty big. And hard drives used to be the size of refrigerators back in the 1960s and 50s, you know? And now we have an SD card that's smaller than your fingernail, with more storage on it now than existed in all of computing history up to like the mid 60s on one individual fingernail-sized storage medium. So the whole point of compression is to take that data and squeeze it down. But there's a lot of trade-offs for that, okay? So let's talk about why. So why do we compress? Well, let's look at uncompressed 4K, all right? So this is an example. Now we're going to use the math. I'm going to use I'm going to use decimal numbers, because if we did this in binary, people would be totally gone, I'm sure, as would I. But let's take some facts. Uncompressed 4K. So the first thing I've done is I've chosen a smaller version of 4K. That is the 16 by 9 aspect ratio 4K in home television. Okay, so alert to those of you out there that are buying 4K equipment, make sure that it's true 4K, which is 4,086 pixels or something like that, off the top of my head, by 2160, because 3840 is TV 4K, if you like, and is actually less data, less digits, smaller picture, right? You lose some information. So if you're buying a camera, it should be true 4K. If you're buying a monitor, it should be able to show true 4K, because eventually down the road, this distinction will disappear. We still have this 3840 4K because it's compatible with HD, right? It's still 16 by 9. Anyway, moving on. We have 4K, 3840 by 2160 pixels. That gives us 8,294,400 pixels to play with. We have 30 data bits for color. So we're talking 10-bit color in this situation. We have 3 colors, so 10 bits times 3 colors is 30 bits, right? You multiply the pixels by the bits, and you get 248,832,000 data bits per frame, right? So then how many and you followed that, right? I just want to make sure you got that calculation. So we did how many pixels in the entire frame, single frozen frame, ignore the moving GIF, but single frozen frame, 30 data bits times the number of pixels, 248,832,000 data bits per frame. Okay. Now we divide that by 8 to get storage. If we want to talk about storage, here's our first example of doing storage. Remember, it's an 8-bit word, a byte, right? We want bytes. So we divide that number by 8, we get 31.1 megabytes. So every frame of uncompressed 4K is going to be 31 megabytes, every frame. There's 29.97 frames per second in our example. Remember, so changing the frame rate changes the magnitude. If you double the frame rate to 60 frames per second, you're doubling your storage, right? So don't, and you're doubling your bandwidth as well. So it's not just doubling your storage, it's doubling that 248 million number now. Okay, so you got to watch your bandwidth. So 29.97 frames per second times 31 megabits is 932.19, sorry, megabytes is 932.19 megabytes per second. Right? 932.
Can you say that one part again? So did you say if you double your frame rate?
Yeah, so if you're looking at 29.97 frames per second, this is one of the challenges with high-speed cameras, right? If you double your frame rate, you're doubling your data rate, because one frame of frozen image, because remember, all video is frozen images. If you change the frame rate, you increase the data rate. One of the reasons people shoot in 24 frames per second in video for filming and for cinema is because it's a lower frame rate. It actually saves space. It reduces bandwidth. It has advantages. It's the exact same reason they shot it in film. They picked the lowest possible frame rate in film to save money. You could shoot film at any rate, but the more you use for film, the more expensive it gets. So the same is true with video. So I'll go back again. 248, 830, 200 is one single 4K progressive frame. If you go 2997, which is your standard frame rate for broadcast, you get 31 megabits, which is that frame, times the frame rate, you end up with 932 million bytes per second, 932 megabytes per second. Okay, so that's why just changing your frame rate cavalierly can have impact on storage and data. Not to say you shouldn't, I'm just saying understand what happens when you do those things. It prepares you for disappointment. If you're shooting something in 60 frames, let's say, and then you go to edit it and your computer bogs, why is that bogging? Well, because you've doubled your data. And is it worth it, right? That's a question you have to ask yourself. Do I need that frame rate? Anyway, moving on. So in a 2997 frame per second environment, you end up with 1,798 frames a minute. So you can figure out you've got 55 gigabytes per minute of 4K, uncompressed 4K. All right. So if you don't compress, you get hosed because the equipment can't handle those kind of data rates yet. We're getting there. I mean, it's probably within reach now that we can start shooting and working uncompressed, but it's expensive. Shooting things like RAW are still pricey. Remember, price, speed, quality. So it's either more time, more money, or don't shoot RAW. But if you don't compress, you get hosed. And I say that because there is a term called the data fire hose. And that is an unending stream of data that gets out of hand. You just keep spraying and spraying and spraying, and it just knocks you back. So let me just show you the work again, because I know people are probably scratching their heads. How did I get that number? Remember, the uncompressed video has a constant bit rate, and what that means is the same amount of data every second all the time. So that's an important thing to remember. We calculate this by going color depth. How many bits per the color? Remember, we said 10 bits, 3 colors, 30 bits altogether. We multiply that by the vertical resolution, the pixels up and down. We multiply that by horizontal resolution and the frame rate. Now, there's tons of online calculators. If you want to do a Google of video data storage calculator or video data bandwidth calculator, you'll find a whole bunch of results that show you how to do this very quickly. It's quite handy sometimes. There's actually an app. I have an app on my phone. I think it's Aja. Let me just double check. Let me just double check. I'm double checking in front of you, which I shouldn't be doing here. Hang on, my work apps. Yeah, so you know what I'll do? I'll stop share, and find the app. Here it is. Okay, so this guy here, I don't know if you can see that. Aja data calculator. You guys see that? And it'll let you do all kinds of storage calculations. You can figure out what your resolution is going to be. It'll tell you if you're NTSC or if you're, that's reversed, isn't it? Anyway.
And what's the app name?
It's called Aja, AJA. Here, AJA, I'm trying to get the glare of the light off of it.
Yeah, okay, thank you.
Aja data calculator. It's a free app on Apple, the App Store. It might also exist in the Google Play, but it's super handy because it lets you do some really quick calculations. You know, for example, if I take, it actually has devices in it too, right? So if you say a certain camera, but let's just say 8-bit NTSC, 1 hour is going to be 37 gigs. So that's 8-bit standard def. If I go HD and change this to HD 1080, I'm going to have 223 gigabits per second at 8-bit color, right? And on and on. So that's a handy tool, but it's important to understand how this tool works. So, you know, listen on, and we'll carry on with this. So let's go back to share. Here and share. All right. So because I stopped, I'll just go back. Color depth, how many bits for the color, times vertical lines of pixels up and down, times horizontal across, times frame rate. 1024 values for each color. We'll get to that later on, but don't worry about that right now. 10-bit red, 10-bit green, 10-bit blue. Remember, there's 3 subpixels. That's why we have 3 different bit values. There's not 1 pixel for all 3 colors, right? Talked about that before. There's 3 subpixels, so we have to give each one a value. That's 30 bits of data per pixel. Per pixel, multiplied by the pixels, right? So here's the math. And I won't go through everything because I just realized this goes off the edge of the frame. Multiply by the pixels, get the number. Multiply by the frame rate, get the pixels per second. And then multiply by bit depth to get the number of bits per second. All right, so that's how the work's done. And then at the end, divide by 8 for storage. So if you need to know bandwidth, if you're, for example, doing something on your home internet, and if you've got an internet bandwidth calculator, another tool you can get, by the way, is a utility, and I think I've got one, I forget the name of it, but it allows you to see how fast your internet is. You've all seen like Ookla speed test and things like that. So here's a situation where in our industry now, that number is important. If you've got a, excuse me, if you run a speed test on your internet connection from your Wi-Fi and you find you're only getting 1 megabit per second, right? You can see already that we're at 7 megabits per second in this calculation that we did, 7.457, right? If you do the math on that first line. Well, your data is not going to fit. So then you say to yourself, well, how do I get higher speed? And this is, again, a thing you need to learn. You have to say to your producer, well, you know what? We can do this, but it can't be on Wi-Fi. We're only going to get 1 megabit per second on the Wi-Fi. If I plug in an Ethernet cable to my laptop, I'll get 15 megabits per second. Right? So you're asking about practical applications for some of this. That's one of the big ones. And a lot of people assume it's just magic and that the internet just works, and then it just doesn't work, and it's flaky and it's unreliable. You know what I'm saying? Like you get all these things because what you try to do is you try to pound too much data through the goose, and the goose dies. And so, well, you know what? I can't do video on the internet. It's flaky. No, check why. Why is that? Because you tried to send 7 megabits per second uncompressed 4K down Wi-Fi, and your Wi-Fi connection in your house is really dependent on how close you are. Like I'm 15 feet away from my router down here, and I'm probably at half the data rate, maybe less than half the data rate of my internet connection. Right, and on top of that, Wi-Fi itself slows it down, even if it wasn't. Even if it was perfect, which it isn't. So Wi-Fi is already slower than a cable connection. So the point is that as a technology person, you can solve your problem by saying, you know what, I can't do this from here with Wi-Fi, but if you get me 50 feet of Ethernet cable, I can get you 15 megabits per second, and we can go live tomorrow, today, right now, right? So that's one of the reasons why you need to know this, because you're going to be asked these questions, some of you, anyway. All right, so you've got the bandwidth calculation on the first line there, the 7.4 bits per second. That's your bandwidth. So, and by the way, remember interlace? Anyone? Interlace takes that 7.4 number and cuts it in half. Why? Because it divides the picture in half. So now your biggest chunk is half that size. So remember that we're talking about a progressive frame here. This is the frame size, 7.457, right? So it never gets any smaller than that, because that's an entire frame. But interlace is a trick, and this is why we use interlace still, because it lets you take that number, and if you interlace the data, you're still getting the same amount of data per second, right? Because it's 2 chunks together. But the point is you can take those chunks and cut them in half. So you're only at one time having 3.2 something, 3.2 megabits per second. No, sorry, 3.2 megabits at a time. It's still 7.4 megabits at a second, but the width, the literal width of your band doesn't have to be 7.5. It can only be 3.5. So interlace is one way to get around a bandwidth restriction, right? Because bandwidth isn't measured, although it's measured in per second, it actually is the actual width of data going through at any one instant. And the smallest amount of data that goes through in any instant on a progressive frame is the whole frame. Right? But in an interlace frame, it's half the frame. So that's one of the reasons why interlace still has a bit of value. Anyway, before I wander off too far and confuse you too much, then we divide that number by 8 bits to turn into bytes, because storage is measured in bytes, and we have 900 megabytes per second. All right. Now, we're not done, because all that was just the video. The reason that we don't worry too much about the other things is because the numbers are so small. Like audio bandwidth is something in the neighborhood of 100K, 50K. So when you're talking megabits versus a couple of thousand extra bits for audio, no big deal. Same with the metadata like time code and closed captioning, right? That's not really significant. Those are numbers that you have to think about. But so here's my question. My point to you is, because audio files don't get particularly large compared to video files, always use audio uncompressed. Don't compress your audio unless you have to, because it won't make a difference. When you're looking at this number here, 74574955040, and you change that 495 to what's the number I could pick? Let's even say you go 7457 600 040. If you have maximum audio, you can see that 7.4 is still 7.4. So it doesn't make a big difference, right? So audio files audio bandwidth can be big, which is the bonus now of more paths and more bandwidth that we didn't used to have. Okay, and the other thing, so the frame rates, keeping in mind that frame rates have a significant, well, can have a significant effect on your data rate. Okay. All right, so it's going to be a lot of data. That's the bottom line here. All that is a way of telling you there's going to be a lot of data going on. So we need to compress this data, right? Why do we have to compress the data? Limitations of bandwidth, like I talked about Wi-Fi. You know, if you're going to use Wi-Fi, you need more compression. YouTube is a classic example. YouTube compresses stuff dynamically based on what you're receiving. They do a quick measurement of what you can receive when you hit play, and it adjusts the output bandwidth to suit, or it can anyway. The size of storage you have available. How much storage have you got? Right? You might want to shoot the highest quality video you have in the world, but you don't have enough storage. So now you've got to compress more. How much your hardware can compress and cope, right? Et cetera, et cetera. How do you achieve compression? Okay, the first thing you do is you get rid of what's called irrelevant data. And irrelevant data is information that we can't see or hear. Remember, we're very sensitive to contrast information for our eyes, but we don't see colors very well. And you know, green is more sensitive to red and blue. So we can play tricks with the math and get rid of those things. It's also called perceptually unimportant information. It's stuff we wouldn't miss if it was gone. The other way to do it is reduce redundancy. In other words, get rid of stuff we've already captured. This is the key of MPEG. And what MPEG does is it calculates using adjacent pixels or frames. And if we've already captured that information, it just doesn't capture it again. And we'll explain a bit about that in a minute. You can reduce the number of colors, right? Change your bit depth. If you haven't got enough data space, change your bit depth from 10 to 8. Lower your frame rate, right? Audio redundancy, et cetera, et cetera. There's all kinds of ways you can get rid of information that we don't, this is irrelevant information that we don't notice. So when we talk about redundancy, and that's the information that we already have, this isn't the same. So I want to go back and be clear. We talked about irrelevancy. That's information that we cannot detect. So audio frequencies, for example, above human hearing, we can discard those because we're never going to hear them. That is irrelevancy, right? Perceptually unimportant. Redundancy doesn't matter if it's relevant, we've already captured it. And we're going to do some math to get rid of the data and then restore it later, okay? So we're going to talk about redundancy now. And there's basically two kinds of redundancy. There's spatial, which means pixels that are nearby each other in the same frame. And there's temporal, which means frames that are nearby each other in time that have similar content. So, and you know, it's hard to show this in colors without having video at the same time. I'll run a video in a second, but spatial happens inside each frame. And that's called intra-frame, within the frame, like intramural sports at school, right? It's teams from the same school competing with each other. So intra-frame compression, like, for example, JPEG. Okay, JPEG is an intra-frame compression scheme because all the compressing happens within one frame. You don't need any other frames for JPEG to work, right? It all happens in the same frame. So how you do it by not recording data in adjacent pixels. And that data, because it's visual data, is either color or luminance. So what we do is we record the fact that the pixels are the same. So here's an example, and it's a really crappy one because, of course, we're on the internet, it's hard to see. But if you imagine that in that highlighted square, all those pixels are the same color, all that the compression scheme would do is record the one on the top left and say, okay, because remember, pictures scan from the top down. That's why I picked the top left. So the top left corner of that red square would be recorded. And then it would just say to the computer, it would say in the code, all the rest of these squares are identical. Okay, and that's it. And then basically what it's saying is don't record anything else until we get to a different color. Okay, so store the first pixel and then repeat that pixel until the change occurs. Now you can already see that's going to cause you some trouble probably because it's not an exact copy. We're not copying. Remember, this is digital. We're not copying reality so much as we are mathematically calculating reality. So here's how that would work. The first line has 4 pixels with these values, but the 5th one is different, right? And again, you probably, I don't know if you can see the color differences on your Zoom at home, but they are different. And you'll see it when you look at the slide presentations online. So here's how you'd record that. You'd have the 4 color values in 1, 2, 3, and 4, and then a different color value in 5, right? So that's what the actual data is. But this is what you'd record. Record the first one, and then just say repeat 1, repeat 2, repeat 3. Okay, and the thing is, because that repeat 1, 2, and 3 is not real world information, it's not stored, it's math. And the math is saying pixel 1, and then change when the pixel changes. And so it just keeps repeating the first pixel until it's told to change. So those in between ones that say repeat 1, 2, and 3, that information isn't stored anywhere. So now you've taken 5 squares, 5 pixels, and you only have 2 bits, right? You've only got 2 information bits out of this whole thing. I shouldn't say bits, I'm sorry, 2 data points. It's actually more than 2 bits. You've got 2 data points out of 5. So you've saved 3 data points for use in something else, okay? So that's called spatial redundancy, and that's a very common method used in all compression, all right? When it's ineffective is when you've got high resolution images or a busy scene. For example, a classic example is snow. When you shoot a picture and it's snowing, this even works with still pictures, and the snow is falling and everything in the scene has little snowflakes everywhere, that means a lot of the pixels are next to pixels that are different. You'll have a white snow blob in the background, then a white snow blob in the background, which means you don't have a lot of adjacent pixels that are the same. And that data there's going to be more data there. So spatial redundancy won't be as effective. And you'll either get one of 2 things will happen. Either the file gets bigger if the software automatically compensates for the extra data, or you lose information because you just don't store it, right? And then it looks fake. And you guys have all seen blocky images and stuff that looks kind of fake, right? The second kind is called temporal redundancy, and this is from the Latin tempo, meaning time. And what that means is that the things that are redundant over time. This only works with video. So JPEG will work with a still image, but also with video, right? You can use JPEG to have video compression. There is what's called motion JPEG, which is a series of still images individually treated. But a better way to reduce data is between multiple moving frames. And this is called interframe. So between the frames, like intramural sports, teams from different schools competing. Okay, the trick is interframe compression is you have to have a group of frames to compare. So again, the first thing we do is we come up with a number, and the original number of groups was 8 because 8 is always a good number of computers for some reason. And we have either 8 by 8 groups or 16 by 16 groups in clusters of pixels. And we also have a series of frames. So there's 2 things going on, right? We have a series of frames called a group of pictures, GOP. And you might have seen long GOP or long GOP referred to in the literature. And we also have a cluster of pixels inside the frame. So I think here is, you know what I'm going to do? I think I'm going to show you a video. Let me just pause the recording for a second. I think. Okay, so he talked about the math. I'm going to skip a bunch of the slides because he kind of covered some of that stuff in that we're not recording data that's similar across adjacent frames. What we're looking at, and what I want to show you in a couple of these slides here are these red squares with the black squiggly lines, right? And what these black squiggly lines and red squares are showing us is the direction, the mathematical calculations of the direction that the frame has come from compared to the previous frame and where it's going to. So any frame in this image that does not have a red square in it is not being recorded because it hasn't moved from the previous frame, right? So either the person has moved. So obviously in the case of this frame, you'll notice that the objects in the background, this, I guess that's a building or a window or something, you'll see little dots and stuff. There's the occasional frame has changed, but there's very little motion. The person, because people tend to move, you'll see the long black lines have turned, or the lines have turned into long lines and squiggles. Those lines and squiggles describe the motion of that person since the previous frame. Okay, so that's part of the calculation that's being done. And all the white areas are not being recorded because we've already recorded them once in this string of frames. So here's the second frame now after that, and it's moved again, right? And I've highlighted again the red frames. Excuse me. Moving on. Okay, so this, I'm just repeating what I've said. These black lines show the direction of motion, and the arrows are showing, you know, the arrows in the black line show the direction of motion from the previous frame, and that's what's being recorded. So my point is, we're recording a little bit of actual real-time data, but we're also recording a bunch of math. Okay, and you can see that the white area is not being recorded; it's being calculated. And a good compression scheme, and this is where choosing compression schemes like MPEG, you know, whatever, is important, because a good compression scheme can do this calculation really well, and a poor compression scheme doesn't do this calculation well at all. Okay, so here's a close-up just to see. You can see the line, the arrowheads, right? And where the motion's going down and left and right. So when is it ineffective? As Tom pointed out, lots of scene changes, lots of motion, fast motion. That's when temporal redundancy breaks down. What's the key to temporal redundancy is the group of pictures. So when we talk about comparing frames, we're not comparing all the frames in the video at once. We're comparing in chunks, because again, computers, we love chunks. MPEG is a very famous group of video, a group of pictures style compression scheme. And it's created by the Moving Pictures Experts Group. They're the standards people behind MPEG, and there's MPEG 1, 2, 4, 7. The trivia about MPEG 3 was it was designed as a video compressor scheme. It never got completed in time. MPEG 4 came up before it was done, and they released the audio portion as an audio file. The key point to these motion compression schemes is they have to identify certain frames. And I'm going to show a picture now because it's getting too abstract. This, if you imagine these colored squares are 8 frames. Is that right? I'm just going to double check here. There should be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So there's 9 frames. There's 8 frames in one group, and then the 9th frame from another group, right? So you've got this 8-frame group of pictures, and these are the frames that are compared. And then you start again. So everywhere you see an iframe, and this is what's important about iframe compression. Wherever you see an iframe, that's an actual piece of video that's been captured. This is right off the sensor. This iframe here is off the sensor. Every other frame in this string of frames is math-based, some more than others, right? So the P frames and the B frames are calculated from the iframes, and you record a brand new fresh iframe every 8 frames. And that would be called an 8-frame group of pictures. Some HD codecs use a 15-frame group of pictures, also called long GOP. And that just means there's 15 calculated frames, or actually 14 calculated frames between every real frame. The problem with this process is that when you want to edit in here, you can only edit on an iframe. So you have to create a new iframe whenever you want to edit. Okay, so here's a quick illustration. The iframe is all video, no calculations. It could stand on its own. You could pull out an iframe out and show it on the screen, and there it is. A P frame needs previously coded frames. In other words, it needs a frame before it in order to exist. The B frame calculates the frame before and after. Okay, and this is one of the things that contributes to digital lag, is we have to hold the video until we have 8 frames recorded before we can start compressing. Okay, so that sometimes there's a 7 or 8 frame delay. That's why. That's how the B frame, it doesn't look into the future at the next frame. It waits until that frame is recorded and then begins calculating itself. So as you can see, there's tons of math going on, right? And here's an example of frames being built. Right, you start with an iframe, which is all the pixels, and then all these intermediate frames do various calculations to create themselves. And don't worry if you're not getting it today, because we will pick this up again next week. I'll probably start at this point again, okay? Here's a macro block in motion. So this is what we have here is a head of a football player. That's going to be tracked by the software. So we've put a box around it, and you can see that it moves now. The football player moves, the head moves, the shape of the head changes, there's motion involved. All that data is being collected of that group of pixels. Okay. The compression scheme, iframes are generally compressed internally, like a JPEG, 7:1 roughly. B-frames, because they're all math, they're 50:1. There's very little actual real data to make a B-frame. It's almost all well, it's at least half calculation, if not all calculation. Okay. So, like I said, I know it's getting near the end of the lesson. I don't want to go into too much more depth yet. Just understand that we'll be talking about that next week. We'll pick it up there. Any questions about this? Because that's kind of a lot. Watch the videos. You know what I might do? Well, how much time we got? No, we haven't got enough time. I'll show the videos next week. Watch them now. We'll start the lesson next week with the videos. All right.
What will how many questions are on the quiz?
I think there's 15. I might make it 10 because I didn't get all the way to the end today with a lot of clarity. I could sort of sense the energy of the room vanished about 11:15. So I will go back and have a look at the quiz. It doesn't open for another half an hour. I might delete some of the last questions.
Okay.
I'll move them into next week's. They're not going away. They're just going to next week.
And will you be able to upload the lectures today?
The which, sorry?
Upload the lectures today, like last week. Uploading the lectures you made.
Yes, I'm sorry. Yeah, so my apologies. I extended the quiz deadline because I forgot to upload the lectures. It's part of my new system. I'm using 2 computers, and I completely forgot that my lectures were on a different PC. They were on my PC, not my Mac. So when I went looking for them, I thought, oh, I guess I must have forgot to record them. No, a generous student reminded me that they weren't there, and I found them. And now I know, of course, where they are. And I knew where they were before. I shouldn't say I didn't know where they were. I don't want to sound like an idiot. But I'm not into the habit of using 2 computers, so I know it's on the computer right in front of me right now, and I will start the upload immediately after this lesson. And in the meantime, I'll work on the quiz. So I got some work to do for myself. Okay, that's all I'm going to talk about today. Any questions? You got a couple more minutes of my time before the meter runs out. Questions, comments, industry tips. So if anybody wants to understand more about this, like I said, look at the videos. There's a whole bunch of videos. I'm not going to show them all anyway next week. And it would help you to look at them now. I won't say very few. The editors in the room will probably use the most of this, because when you're talking outputting compression and data compression, it's easy at the beginning just to guess and use presets, but somewhere down the road in your career, you're going to have to start making decisions that are outside the presets. The presets aren't going to work for you. So for example, I've tried to upload a couple of my lectures in the past using YouTube presets. They don't work. So I've got to go into the media encoder and start monkeying around with settings. And I've got to know what I'm doing. Like if I'm doing a color lecture, as an example, I don't want to change the color depth of my video. So I've got to maintain my color depth. So that has to be manually adjusted, right? So those are the kind of things that will become important for you. If you're doing stuff where it's just test footage, but if it's a makeup test, if you want to see how someone looks in a certain makeup, again, color depth and resolution are really important. So then your decision is, do I shorten the length of the clip? What can I adjust? Or maybe I don't even bother compressing. I just email it to the person, right? So this is the kind of decision you're going to make. And we'll talk more about that next week. For some of you, you'll never deal with this again. I mean, this will be the first and last time you'll have to deal with it. It all depends on where you're going. And of course, I don't know where you're all going. And maybe you don't either. But editors and colorists particularly are going to want to know about bandwidth. People doing broadcasting, like live streaming, running, internet interfaces like Gero boxes and other things, are going to want to have an understanding of bandwidth. So that's kind of where this is going to come into your future. And also, whether you go to another resolution, right? Do you bother going 8K? Is it going to just cost you too much money, right? And we're talking about that right now as a faculty, about the program, choosing what resolution do we choose for the future. Well, the problem with choosing a resolution is out of hand. Like all the kids are using 8K as a comment is great, except that's for us, that could be hundreds of thousands of dollars in change to hardware, because everything has to be adaptable, right? And you're not going to have that same magnitude decision, but you're going to have an issue with, is your laptop fast enough? Do you have enough storage? You've gone from HD to 4K. You've suddenly quadrupled the amount of data you're going to need. On and on and on it goes, right? So that's kind of me trying to put it in some context. I hope that helps. I hope it assures you that it's not a fatal flaw not to get this.
I think it'd be helpful if there was like a link to a lot of the glossary terms, like.
Good point. Yeah, I can do that. I can put together a little glossary for this lesson. And in fact, you know what we'll do? That's a very good idea. What I'll do is we'll start next week with the videos and some words.
That'd be great.
Yeah, we'll do that. I've actually got a glossary somewhere that I was going to give you guys as a test. It's 64 pages because it's 64 words. But you know what? That's not going to work. So, but I will. I'll take some of these terms and we'll go over them again. And like I said, don't worry. I know I recognize the time. You know, we're now down to the last couple of minutes here. I feel like it's New Year's Eve and the ball's going to drop. But I do recognize the fact that I can't squeeze this all in detail. And it's a very difficult concept to get without being there and showing you stuff. Like the challenge with this is a very visual lecture and visual to the point of actually looking at pixels. And the problem with our connection is I cannot get that kind of resolution across to you through Zoom. Whereas in a classroom, I can put it up on a monitor and I can stand there and point at stuff, right? Because the monitor can show the stuff. The Zoom, I don't have a lot of faith. I mean, I'm looking at my own playback on the other screen and it's not even in real time. It's a slightly delayed in my own room. So I can't imagine what you're seeing at your end. So yeah, there'll be a glossary, there'll be videos, there'll be fewer quiz questions. Let's just make it like 10 right now. I'll say it's 10. And you guys have a good week.
Thank you so much.
All right.
Thank you.
Welcome. See you again.
Thank you.